Good afternoon, everyone. Welcome to the webinar. We're going to give just a couple of minutes to let everybody get connected. But I'll just tell you, my name is brandy.nussbaum, and I'm the sales director at ANOxKaldnes, which is part of Veolia Water Technologies. I'm actually joining you today from a small island off the south coast of Sweden, where ANOxKaldnes is located, and I'm speaking to you from a little cozy hotel room. And I'm joined today by my colleague, Romain,
hello.
who is sitting in France. How are you today, Romain?
Pretty good, thank you. Sitting at home today, not in the office, so in a little village in the Loire Valley, not far from the castle and the vineyard, so better
Nice.
than in the office.
Nice. So it's a nice early morning here in Sweden and France, but we also have our colleague, or our partner here on the webinar, Justin from Urban Utilities, a local boy there in Australia. Justin, how are you today?
Yeah, well, thank you. Yeah, so I'm actually presenting from one of our second largest treatment plant, Oxley. It's a nice little place. Yeah.
Nice. So it's great that we can come together from all different parts of the world to present this webinar. So I hope that we have given enough time for everybody to get connected. And I would once again like to welcome you to this SUPERBUGS Revolution webinar. Those of you who missed the introduction, my name is brandy.nussbaum. I'm the sales director at AnoxKaldnes. AnoxKaldnes is a Veolia Water Technologies company located in the south of Sweden, and we're the technology experts for the solutions that you're going to hear about in the webinar today. And I'm joined in this webinar by romain.lemaire, who is a biological and process expert also at Veolia, and also Justin.todhunter, who is an operations specialist from Urban Utilities. And you're going to hear from these two experts for the bulk of the presentation. In the next slide here, I just want to do a little bit of a webinar housekeeping, normal things. You guys have heard them before. You're going to use the questions function to ask your questions. So look for the little question mark or the questions word there, and you can type your questions, and we'll look at those as we go through the presentation if we can, or we'll address them at the end. You can choose your preferred viewing option in the gallery or in speaker view. And you are automatically muted, but if for some reason it's not working, just go ahead and mute yourself to not disrupt the rest of the presentation. As I've already said, the focus of today's webinar is the SUPERBUGS Revolution ANIMOX webinar. And the Veolia Water Technologies ANIMOX solution is called ANITAMOX. And it has arrived in Australia in the form of a first full-scale reference that you're going to hear about from Justin, and also as a local biofarm that can be used to start up new ANIMOX or ANITAMOX solutions there in Australia. So what makes ANITAMOX so exciting, and why are we here to talk about it today? I want to leave you with just these sort of 5 take-home points before I turn it over to Justin and to Romain to really give you the meat of the presentation. But just as take-home messages, now with more than 12 years of experience and 40 full-scale references, we know that our Anammox solution, ANITAMOX, is proven, it's proven sustainable, and we know that it's going to save you money. We know this over these decades of experience that we have using this solution. And also with our local expertise there in Australia with Veolia Water Technologies Australia, and the global support network that we have with ourselves here at AnoxKaldnes in Sweden, the team in Paris with Veolia and Romain, we know with our advice, it's easy to install and easy to operate. But I think you're going to hear so much more about that in the coming slides. And with that, I'm going to turn it over to Romain. Oh, actually, sorry, to Justin.
Good. All right. Thank you very much, Brandy. Look, I just want to start off with a bit of context as to why we ended up obviously selecting the ANITAMOX technology, and really the key drivers for us as well, obviously a wastewater and water utility, to really pursue these alternative strategies for obviously providing really good benefits in terms of wastewater treatment. So who are we? Urban Utilities, as mentioned, are a water and wastewater utility. So we own and operate about 26 treatment plants across 5 different councils that fall within the majority of the Brisbane River catchment. These flows end up ultimately in Moreton Bay, which is a very environmentally insignificant area that supports a vast array of marine life within the southeast Queensland. Thus, the nutrient emissions from our plants therefore play a really important role in maintaining the health of the bay. And with expected population growth and changes to the catchment characteristics, such as industrial loads and water profile and COVID, apparently, urban utilities really does always face these increasing pressures on really trying to balance these nutrients, emissions, operational costs, and treatment capacity. Next, please. So as mentioned, with these increased pressures on wastewater utilities, not just urban utilities, to accommodate these population growth, there's always a pursuit of, there's also, in addition to the population growth, there's always a pursuit of lower nutrient targets to obviously improve our waterways. And therefore, it's better to understand a lot of these social and economic impacts that these drivers really have on our customers, essentially. And whilst there are various options to improve effluent targets through capital and operational investments, most of these traditional upgrades really do conflict with the strategy of sustainable treatment due to the almost increased cost to the customer. And so urban utilities really taken on the strides to invest and look at these alternative strategies. And the one that we're speaking today is obviously AnammoX, which is fantastic. Next, please. So just giving a bit of history around Brisbane and the Brisbane River catchment, urban utilities introduced a bubble license back in 2016, which was the first of its kind for the Brisbane River catchment. And compared to traditional effluent limits for individual STPs, the permit really allows urban utilities to operate 9 treatment plants, as located on the image, to combine the total mass load for both nitrogen and phosphorus. And whilst whilst the implementation of the bubble license has presented both a risk, or it does present both a risk and an opportunity to achieve greater emission reduction by shifting attention from your smaller plants to your larger plants. And this obviously has a cost benefit to it as well with scale of economics. It also does provide a bit of a risk. And for example, Luggage Point being such a large plant and contributing such a large amount to the bubble license of the mass load to the bay, a change of 1 milligram per litre in the TN from that plant effectively is equivalent to about 50 tonnes of nitrogen per year, which is pretty substantial. Next, please. So this is essentially why we've, urban utilities has focused a lot on this large treatment plant, which is Luggage Point. And it is expected that the population will increase quite substantially. There has been interestingly enough, there has been a bit of a bump with COVID, with shifting in population and changes in industrial loads to the plant, which is obviously important for this situation because you have to become flexible within your treating options to really deal with these kind of changes. And so, while there's projected growth, we've done a lot for continual improvement to provide better, obviously, effluent. A lot of this work ends up becoming diminishing returns. The more you invest, the less, the minor the change, the smaller the change that occurs at the treatment plant. And so, as I mentioned, whilst there's options to really meet these effluent targets through capital and operational investments, most of these options do conflict with our sustainable, our strategy of sustainable treatment, which has that ultimate, that almost certain increase to the customer. And so, next, please. And so what this means for us is, we ultimately have to invest in infrastructure or increase operating costs to manage these environmental impacts. Next, please. Sorry. So just a bit of history, or just a bit of a summary on Luggage Point. It's our largest treatment plant. We have 6 anaerobic digesters where we redirect carbon towards our digesters. Apologies, sorry. And whilst this provides a lot of benefit in terms of renewable energy on site, it does provide a lot of load back to the head of the plant, which is equivalent to about 12 to 15% of the plant's return, which means that this contributes to a lot of the ethanol or the chemical and air usage within the plant. And therefore, we went along the route of, next please. And that's why Urban Utilities started the review of looking at options assessment for reducing this Sidestream load to the head of the plant to improve our operational costs. And after several years of testing, we did an options assessment across various different types of AnammoX technologies. Urban Utilities landed with the ANITA MOX technology, which we've been really, really happy with to date. And I'll allow Romain to really continue along just to give a bit of a background more on the technology and AnammoX itself. Thank you.
Thank you, Justin. And Justin will be back to show you a lot of the results and of the ANITAMOX in Luggage Point. But in the middle, I will give you a bit of a intro and of the ANITAMOX technology itself. So when we talk about ANAMOX versus conventional processes for nitrogen removal, the conventional processes are using a lot of oxygen to go up to oxidize ammonia to nitrate, and then a lot of COD to go down to denatrify. So that's a big mountain. When we look at ANAMOX, the mountain is much not as high, a bit like Uluru in Australia, because we need less oxygen, so we can save 60% of the oxygen, because we don't need to oxidize all the ammonia into nitrate anymore. We just stop to nitrite, and only 50% of the ammonia. And with the remaining ammonia, the ANAMOX bacteria can remove everything to nitrogen gas, no need of carbon. So less oxygen and no carbon required, which is great for Sidestream treatment from anaerobic digestion. Next, please, Brandy. So the process itself is based on MBBR, so moving bed biofilm reactor. So in these processes, we have quite simple. We have a tank, we have a carrier, media to support the biofilm, the ANAMOX in our case, and an nitrifier, both population. So you see some blown picture in there, and you have the media and the biofilm. And we have an oxygen, we apply an oxygen level which penetrate into the biofilm, but not fully. So we create 2 zones in the biofilm simultaneously, aerobic zone on the outskirts of the biofilm, and an deep anoxic zone deep in the biofilm. And that will make the bugs to locate themselves automatically. For the nitrifier, they will be in the outskirts when oxygen is available. They will nitrify the ammonia to nitrite, and this nitrite will then diffuse deeper in the layer of the biofilm to the ANAMOX. They don't like oxygen, so they're way below the nitrifier. And they will then remove the remaining ammonia and the nitrite produced by the nitrifier to do the full denitrification and ammonia removal. So that's the principle, and that's actually what happened in reality in the ANITAMOX. So when we look at the process itself, basically we have one tank, very simple, flow coming in, flow coming out. In the case of Luggage Point, there is even no buffer tank after the centrifuge. It directly go directly in the tank. Usually we do have a bit of an EQ tank to equalize a bit based on the dewatering operation on site. But it's flow in, flow out, no decantation, no settling of the biomass. Everything is attached on the media. And to get the media, the ANAMOX, which are a slow grower, to retain in the system, we just rely on the physical barrier, which is for MBBR, a grid with little holes so the water can go through, but not the media with the prime ANAMOX bacteria on it. Okay, so it's the pure 100% retention capacity MBBR, of all these bacteria. And you can see on the photo that all the media are on the grid, and there is no way it can leave the system. So no risk of losing the Anammox biomass with this MBBR configuration. And also, quite important, no impact of incoming TSS, because we all know that centrifuges go berserk sometime in operation. That's the reality. And if you have a big spurge of MLSS or TSS coming out, it will come out by itself, and it's not going to impact too much the system. So it's a clear difference with some granular system which rely on the granular and settling facilities on the granule. Then the TSS coming in can become a bit of an issue to separate the granule and the suspended sludge. Next slide, please. In terms of reference of ANITAMOX so far, we are a bit over 35 today. Most of them are located in Europe, as you can see, spread in between the Scandinavia, France, the UK, in Poland, in Switzerland, in Slovenia, in Ireland, in Denmark, in Norway as well. And we also got few in the US. It's been, on the ANAMOX market, the US is moving since quite a while now. And you can see that we're really proud to have one on the other side of the world in Australia, so in Brisbane. So that's a map at the moment for a reference. We started pretty much, the first one was in 2010. So it's a bit more than 10 years that the ANITAMOX has been successfully implemented worldwide. Next slide, please. So I will show you a few little example of some of our reference. So the first one is the one in Denver in the US. I picked that one because it's a larger ANITAMOX today that we have. So it's a very big plant in Denver, almost 2 million PE plant. Started in 2017 for the ANITAMOX, and we've just been reusing existing tanks. So that's a good feature of the MBBR configuration, is like we can pretty much reuse whatever volume you have available. That's what happened in Luggage Point as well. So yeah, they had, you see at the bottom, like 3 tanks that they could reuse, not really being used at the moment in Denver, and we put the ANITAMOX in there. Next slide, please. So you have a few photos on the next slide of the actual construction work on retrofitting some existing tanks. So the water height was not perfect. Like if we have done a new project, we'll probably have higher tanks and so on, but it can really fit into those type of tanks. So in the case of Denver, we have 2 parallel tank of 2,000 cubic meter each. And the alkalinity was limited. We knew that, the client knew that from his centrate, because he's using a bit of ferric for dewatering. And therefore, we knew that we will be limited in the amount of ammonia removal we could achieve if we don't want to add caustic or alkalinity. And the client didn't want to add any. So therefore, the target was more around 75 ammonia removal, which is a bit lower than what we achieve if the alkalinity is not limiting in the system. Next slide. So that shows you the startup period and the performance. So you see that we started this big plant with only 5% of seed media. So we put, usually when we start an ANITAMOX, we put a bit of media with Anammox bacteria already on it, and the rest is virgin media. In the case of Denver, due to its size, we just put 5% of seeded media at T0 when we started. And you see that it took around 3 months to reach the design rate and even to go above the 4 ton of ammonia removal per day. So the startup was pretty quick, the colonization of the new media and the ramp up. And it's been achieving, above par, above the design rate for quite a long time now. And as I say, achieving a removal lower than the usual 80 to 90% ammonia removal, again, due to the alkalinity limitation they had in the centrate. Next slide, please. Another example is a plan we recently, one before, or maybe we can skip that one, which is the time. You're right. If we move to the IFAS configuration, that's when we deal with THP, so with thermal hydrolysis processes, we have to change a bit, and we learn that also with the time. We have to change a bit the configuration of the ANITAMOX. Instead of being a pure MBBR system, we are putting a settler at the back end, and we are recirculating some of the sludge. Therefore, we have an IFAS system, hybrid system. The Anammox are on the media, and the rest, the nitrifier especially, are on the bulk and not on the media anymore. So with that, it's the best configuration to deal with those THP centrate after thermal hydrolysis, because it creates a centrate which is a bit more toxic. It's got some toxicity in there, and therefore we handle a bit better the system with this configuration. If you look at the reference on THP, we have 5 up and running ANITAMOX, and in Sweden, in Denmark, in the UK, in France, and in Ireland, and we have 3 which are ready to be started very soon in Slovenia, and 2 big ones in the US. So we have been on Anammox, Veolia have been the first with the ANITAMOX to treat THP back in 2014 in Sweden. We have 8 projects so far and 5 in operation. And also at Veolia, we have our own THP processes, and we know very well THP and the Anammox. So we are gathering the 2 expertise to provide, I will say, the best design based on your THP centrate you can have on site. Next slide, please. What we've learned also with this THP, and I will show you an example in a minute, is actually it can be a bit more difficult, and we also develop over those years a dedicated digital system, digital control, advanced control system dedicated to the ANITAMOX. So the challenge is, we know we have slow grower with the ANAMOX. We have complex interaction between microorganisms, the nitrifier, the ANAMOX, some heterotroph if there is some COD available, and the centrate variability, and especially with THP, with some feature of toxicity and sometimes higher VFA or COD, push us to develop this type of advanced control system. So the solution is based on a web platform. So we actually are looking online on all the sensor, the instrumentation, and we provide an optimum set point for aeration. And also another feature is the load, the feed to the ANITAMOX, and we look at the level in the buffer tank, and we always adjust the load based on how much centrate is available and the performance of the system. So it's called upgrade, and the benefit for the operator, it's optimize aeration all the time, optimize and stable load to the system based on the condition. And it's a peace of mind and time and cost saving for the operator. And that's also why we developed that over the year to secure the long-term operation of the system. Next slide, please. So you have an example here of the 2 main features, the aeration control. So it's based on reliable instrumentation. It's probably a bit cut at the bottom of the slide, but you will recognize some of those sensors. So we use ammonia, nitrate, pH, DO, and we also have we have reliable nitrite, NO2 sensor also now available, and that helps controlling the aeration. And for the load, we use the level sensor in the buffer tank to better adjust the feed. And also when we have THP, we can also use this feature to optimize the dilution water we need to add to make sure it's not toxic for the system. So the system is not impacting the SCADA of the plant. It's just the operator can always decide to run or not with the upgrade feature, because upgrade is just communicating through an OPC server to the site PLC on site, and it's just reading, getting the data from the PLC, all the information from the sensor, making his own adjustment optimization, and pushing back an optimum set point for the feed and the aeration. If the operator wants to stop, he just have to press a button and he's back to his default set point if he wants. Next slide, please. So Fyford was one of our first THP plant in the UK. So first AnitaMox on the UK being a big market for THP, a lot of big THP plant over there. We started this plant in 2019, and we included upgrade in the middle of the not for the startup, but after a year of operation. I will show you why in a minute. Next slide. So you see here on this graph, so bear with me, the blue is the load, ammonia load applied to the system, and the red is what is removed by the AnitaMox. And the design load for this plant was an 870 kilo of ammonia per day. So you see the line, the blue line at the top. And we have the moving 7 days moving average is the line you see going up and down for the apply and remove load. And the dot are all the actual daily load that the plant received. But we see during the startup, the first 200 days, we had some hiccup with big nitrite events. So a nitrite going a bit up, it did inhibit the system, and we had so we realized, and it took us a bit longer than expected to start that THP plant. And that's how we learned, and we decided to really push for this optimum upgrade operation based on the reliable sensor to improve and stabilize the system. And that's been a bit developed with this project in Fyford. And you see that since we've been treating all the centrate, it's been pretty much stable, and we're pretty close to or sometime over the design load for this plant. Next slide, please. We also, based on this experience, we moved to another plant in Ireland on a THP. So but this time, that was after we started the system with upgrade straight from the start, and so the startup happened in 2021, but the system was a bit quicker to actually get the full colonization and get treating the full load. And it's now continuously operated with upgrade. And this plant is with Irish Water, but Veolia is the operator of this plant in North Boston. Next slide. And the last one is this project in Toulouse in France. So it came also a bit after. So we started in early 2021. So it's a big plant, 1 million PE plant, and the project was to add a full digestion, THP, ANITA MOX on the Sidestream, and so on. So all this project was done by Veolia, all the construction, and you can see the schematic, and then the full-scale realization, and that was for biomethane injection as well for the client, so biopurification, and that has been also started with the IFAS configuration of the ANITAMOX, because it's again a THP. So the plant now has been handed to the client, and it's been running since then. So it's okay for my part. I will then let Justin to conclude with the example of luggage point.
Cool. Thank you very much, Romain. Look, yeah, I just want to give a bit of a brief journey before we share any results around the operation of the full-scale plant, because I think it's really important to just kind of share the journey, because it's been a fantastic one. So as we are aware, I think most people are aware now, it's pretty evident that AnammoX has been, or AnitaMox has been successfully applied operated over the world to treat high-strength ammonia wastewater. I think there's probably more than 110 full-scale installations worldwide now, which is pretty impressive. And we know that the successful and timely implementation of these full-scale operations is really attributed to having that sufficient biomass. But unfortunately for us, being in Australia and strict quarantine regulations, we weren't able to import any of this biomass into Australia. And so therefore we had to start our own journey to actually grow up the bacteria to see the full-scale implementation. And to do this, we had several scale-up enrichment processes, which I'm going to share in a second. Next, please. So the journey actually started actually a while ago, back in 2011, which was before my time at Urban Utilities. This was a partnership between the University of Queensland, creating that initial seed stock. And this was one of the first actual research facilities or projects that actually came into the Innovation Centre, which was a dedicated research facility, which now actually hosts, it's actually grown quite substantially and hosts a lot of local and national and international projects to the value of over $20 million, which is pretty impressive. Always have to give a props to the Innovation Centre, because this is basically where the journey began. And the team in and around the Innovation Centre has been so supportive for this project, which really made it happen. And so, unable to import the bacteria into Australia, Urban Utilities, Veolia, and UQ started growing up this initial biomass. It actually started from a 10-litre jar, laboratory grown AnammoX, and gradually over the years we've kind of built this up to inoculate that full-scale installation. Next, please. So from humble beginnings, I guess, comes big things. We really started at the bare basics. We just had a couple of water tanks. It was pretty agricultural in the Innovation Centre, where we just had basic control of pH, temperature, and DO control. And so we relied heavily on operators and staff to really kind of, make sure that we had, the information we're getting from these tanks to really provide some kind of guidance to obviously direct, what we needed to do or respond to different events that happened. Because we definitely threw everything by the kitchen, and the kitchen sink at this thing, because I think at the time we were also doing a centrifuge upgrade, and so we're just getting high polymer, high TSS, absolutely everything. So it was actually really good to be able to do it in this kind of space with very, very basic control as well, to kind of learn, what's the best way of kind of dealing with these problems. It also gave us a lot of confidence to around the robustness of this technology, which is one of the main reasons why we decided to go with this technology. Next, please. And so one of the final steps in this inoculation period or this enrichment period, we in partnership with Veolia built a 50 cube tank, which we reseeded from the previous water tanks. And so this was actually the first time using this tank where we actually didn't run heating, which was some pretty good learnings, because there was considering the size, there was definitely a lot of fluctuation in temperature between summer and winter, which definitely provided some really good confidence that the technology was going to work in the full scale without heating. And we use this facility basically as a training facility as well, upskilling the operators and building that real confidence in technology for obviously the people that were backing it. And so we had a really great time on trying to work out, implement a bit of smarts from our previous installation, because this was the first time we had some kind of automation. So it was really good to be able to learn a little bit more before we went to design the full scale treatment. Next, please. So the objective of the full scale treatment plant was to provide essentially a low cost upgrade solution for luggage point to accommodate the new full scale Sidestream treatment process. And this was actually achieved by repurposing 4 unused pre-aeration tanks, which required actually a really bit of an innovative design to overcome the hydraulic limitations and shapes because of the shape and configuration of the tank without the aid of mechanical mixing. So Veolia did a fantastic job in being able to provide that technical expertise to be able to retrofit basically these tanks. And so the final solution required kind of altering these tanks to operate in series, consisting of 2 kind of hydraulically connected compartments. But it actually provided a massive benefit for us, because this configuration improved our seeding process, where we only required to seed the front tanks, because the biomass would kind of slough off and move into the back tanks before, which was the effluent. So it meant we only really needed the 5% seeding, and we saw some it was really easy process to seed and grow up. So it was great. Next, please. So the program was assigned in 2019. I think it was one of the fastest projects that we got through, which was really, really impressive. And we later commissioned and installed the ANITA MOX carriers with final seeding of the biomass in January 2021. So it's been, a bit over 2 years now since the installation, and it's still going strong. Next, please. We might just skip through a couple of these. This is kind of the retrofitting of the tanks. So you can see the length of the tanks quite long. So there was definitely some hydraulic, restraints or challenges to make and retrofit these tanks. But yeah, as I said, I did a fantastic job in being able to provide that technical expertise, and it's working really well. Next, please. Yes, and this is when we seeded, added the carriers and the initial commissioning, which was such good fun. It was a really good process. Next, please. I think you can probably just move through the next couple. They're obviously made pretty happy, and yeah, obviously the final installation there. So I think that was probably June, July, 2021. With the carriers, you can see there's a bit of growth happening. So I've got some, it's fully seeded now and operational. So it's been fantastic. Next, please. I might just talk a bit just on this slide, just quickly. Just got to give a shout out to the operators, because essentially this is new technology, and we really had to obviously bring the operators along with the journey for understanding the new system, the optimization, and understand the key drivers. So this is one of our first operators to really look at the technology and try to really work with me to understand how to operate it. And so it's been got to give them the props, because they've done a really good job at taking up this technology and really trying to learn and make it work. So I've got to say a big thank you to them. They've been pretty good. Next, please. So the initial design and expectation for the ANITA MOX plan was to basically treat about 820 kilograms of nitrogen per day. The total reactor volume was around 1,000 meters cubed with about 50% carrier loading rate. So the initial expectation was that we would see about $500,000 of saving through reduction in ethanol and also aeration savings. And the other benefit that we now have is that we've reseeded the biofarm, which we can then obviously provide that seed to other utilities if required for the same process that we went through. Next, please. So the initial kind of expected timeframes, based on obviously conversations with Veolia and other plants around the world, was really within that 3 to 6 months, based on previous experience. We did have a bit of issues. There was a bit of a hydraulic limitation within the plant itself, which kind of restricted the flows for the first 4 months after seeding. But you can see it's kind of entered that exponential phase, which we expected to see in line with other plants around the world. And it wasn't until about 250 days that hydraulic limitation was kind of fixed, and it enabled us to really get up into that to reach out the design treatment capacity. It basically happened within a couple of weeks. So you can see the biomass was there, it was just waiting for the food. So the full-scale implementation or facility now treats successfully over 1,000 cubic meters per day, which is really impressive because this is above the design expectation, and exceeding, obviously, it's actually exceeding the removal rates where we're consistently seeing 85 to 95% removal of ammonium through the process. And so with flows coming in around that 1,000 milligrams per litre to 1,100, it equates to over a load rate of over 1,000 cubic meters a day, where this was designed to do 820. So it's pretty impressive, and it's doing a really great job. And for us, that means that it just means we have extra capacity within the plant. So we're yet to find the total, the actual limit of this plant yet. So yeah, exciting times to come. Thank you. Next. This is just a really good demonstration to kind of show that that time frame just really lines up with that exponential phase. So it was as expected. So it was really good that we were able to see those kind of similar time frames with about a 5% seed. So yeah, thank you. Next. So this is actually a really cool slide because it really this here, the blues our TN results from the plant, and the orange is actually the ethanol. We weren't actually expecting this, but yeah, we've been absolutely stoked with the fact that we've been able to remove all ethanol from the plant and yet still achieve a large reduction in TN. So I think it's about equivalent to about 60 ton reduction without either ethanol dosing, which is fantastic. So this is actually giving us an economic benefit of over, easily over $500,000 per year. So it's obviously gone above our expectation, which is awesome. And I guess it also gives us additional capacity within the plant. And when you talk about capital upgrades and deferral, it adds up to be quite a significant amount when you're looking at the cost of building additional bioreactors. So yeah, it's definitely gone above and beyond what we've expected, and the results have been really great to date, and we're seeing obviously quite a good benefit, which is yeah really good. Next please. So what's in it for us for the future? Well, we're actually still looking at a lot of things to do with AnammoX. We're looking at mainstream AnammoX through the Innovation Centre. We're also looking at utilising additional assets to generate revenue, thereby through co-digestion and importation of high-strength nitrogen. We've still got capacity within the Anammox treatment plant, so we're looking to utilise that obviously really efficient pathway to remove nitrogen to obviously benefit, or get additional revenue to kind of support obviously what we do. There are other options for us to expand within other STPs. So Oxley is the next one. We have a THP unit there, and as demonstrated by Romain, the technology works quite well. We were the first to demonstrate it on THP. So we do have that confidence that we'd be able to implement it at Oxley as well, which is great. Next, please. And so one of the things, just quickly I'll touch on is, if anyone's really had a look at it, the National Waste Policy from 2019, it's kind of expected that we'll be starting to see a lot of these organics kind of shift to treatment plants. And a lot of these will cause obviously changes and drive demand changes within our treatment plants itself for extra infrastructure, tanks, equipment, etc. And we've actually started to commence, next please. And a part of this, we've actually started to commence importation of organics, which now represents about a 10 to 20% increase in digester utilisation. And this benefit, by reducing the cost, well, obviously it reduces the cost if we can bring in that additional revenue. But it ultimately, by increasing gas flows, but it also increases the side stream. So this is where the Anammox process, you want to bring those organics in, they obviously break down and provide more load through the side stream. But if you're providing that load to the most efficient biological process we have in wastewater for nutrient removal, AnammoX or ANITAMOX is the way to go to kind of provide those really good economics for bringing those organics in. If you can just click through, I've just got a few. So that's what I mean. Like you bring organics in, they break down, they release more nutrients, but if we're running it through the AnitaMox process, we're removing those nutrients as efficient as possible. So when it comes to the economics around gate fees and bringing organics in, it really stacks up, which is really great with the technology. Next, please. The other real neat thing that we've actually started to pursue is also importation of high-strength industrial wastewater. As I mentioned, we haven't found the limitation to, or the hydraulic or the mass load limit to the Anammox plant yet, or ANITA MOX plant. And so we're looking at different types of contaminated groundwater. And this is one that we've done recently over the last year, where we're looking at bringing in, I think it's about 10 grams per litre of contaminated ammonium wastewater, and basically adding it to our centrate or that Sidestream return to look at various inhibitions and loading capacities of actually the Anammox plant. And based on some of the work we've been doing with this, we're actually developing a business case to bring in this additional high strength wastewater, which will then be treated through the AnitaMox process as well, which is really fantastic. So yeah, it's really opening up doors for us for these different sources of revenue, and also providing a really good service to various customers within Southeast Queensland. Next, please. Look, finally, I'd just like to really thank everyone that's been a part of this project. It's been a project that's expanded over, 12, 13 years. So in particular, the research and development team with the Innovation Centre, luggage point operating teams, we wouldn't be able to operate and run the plant without their support. The infrastructure delivery procurement teams that have been involved in, obviously, the balance of plant design with Veolia. And finally, Veolia technology has been absolute awesome partner to work with, really supportive, really easy to contact and get that that guidance where we required it. So yeah, it's been a really good journey for all of us. And I'd just like to say thank you very much.
Great. Thank you so much, Romain and Justin, for sharing your expertise and your insights into the superbug revolution, or as we call them, the Anammox bacteria. We do have a couple of questions. The first one, I think, maybe is a little bit of a combination, Justin and Romain. The first question is about the luggage point being a biofarm, and how much seed would be available to take from the luggage point plant to seed another plant in Australia. And then what if you are a biofarm, what would you anticipate to happen in the plant if you take out seed? How do you expect the plant to react?
Sure. Do you want me to answer that one?
Yeah.
Yeah, look, so we actually have the ability to take from our main plant and also biofarm. So we've got a 50 cube biofarm, which has a 50% carrier loading volume. So there's about 25 cubic meters of actually freshly seeded AnitaMox carriers. So we've shown that's demonstrated that's quite easy to seed a 1,000 cubic meter plant, which is pretty substantial in size for treating. I wouldn't expect there to be too much more larger plants within Australia that wouldn't be able to start their process with that amount. But there is also the addition of the main plant as well. There's 487 cubic meters of seeded carriers there, and we'd be fairly confident that you could at least take out 10% of those carriers without seeing any drastic changes to any loading rates to the plant itself. Yeah.
And I do confirm that we've done that in several plants within Europe and in the US to take some seeded carrier from a operating AnitaMox plant, and usually that's what we recommend. Like within taking out 10% of the total media of the system, that's not impacting too much the removal capacity of the plant. And if you add straight after the virgin media to replace those 10%, within a couple of months or sometime even a month, they are fully seeded and back in operation. So in that case, you can do that, and we do that feature or that thing many times on the same plant, like in some of our European or US plants. So that's something that can be easily done. And the fact that, Justin, you have this 50 cube tank on the side, it's also a nice way to provide a bit of seed as well.
Great, thanks. It's nice that Luggage Point was the first ones, and they're there to be able to support the rest of Australia as they move along the Anammox journey. The next question is, I think, more for you, Romain. The question is about the difference between the configurations of ANITAMOX, the high mass and MBBR, and why you would choose one over the other, and is there different equipment involved?
That's a good question. The pure MBBR, so straight, one tank, everything coming in, coming out. This is the configuration we provide when we don't have THP. So, and when for our normal anaerobic centrate, that means when the COD to ammonia ratio is pretty low. So you have a lot of ammonia and not a lot of carbon COD present. When you start having either THP due to this toxicity effect, and also the fact that on THP, because we operate the digester at a lower HRT usually compared to if we don't have THP upfront, we see also more soluble biodegradable COD in the centrate after THP, a bit more VFA, a bit more COD, and therefore the COD to N ratio is a bit higher after THP. So for those reasons, the IFAS configuration is better because it allows, when you have a bit more COD, it allows the heterotroph, so the quick growing organism, the normal bugs which are removing COD, to grow happily on the suspended sludge, and therefore they don't come too much on the media itself and on the biofilm and impact the Anammox growth on the media. So that's why we provide this IFAS configuration. So when you have THP, and also when you have some type of industrial effluent or some municipal plant for thermophilic, for example, which usually have a bit more COD, we will potentially go more toward an IFAS configuration. So it's basically linked to the characteristic of your centrate. Most of the case, that will be MBBR, but not always. In terms of equipment, the tank itself is the same. You have the media, you have the sieve, but you have a bit more sludge because you return some sludge from a downstream clarifier that we provide. It's not a clarifier that you are used to on the normal plant. Like, we are not achieving TSS below 20 or whatever. We just here to thicken a bit of the sludge and be able to return the sludge back in the system to maintain a sludge edge in the system for the nitrifier. So the TSS coming out of that settler is sometimes 100, 200 milligram per liter. It really depends of how much your quality of your centrate. But that's the only piece of equipment. So you get this small clarifier. Hydraulically, it's not big, so it's a small clarifier. You have a scraper and you have a pump. That's pretty much it. Extra equipment you have to provide.
Great. I think we have one more question here for Justin. One quick question, Justin, about the instrumentation that you're using at the Leg Point plant.
Yeah, cool. So actually, this came from a lot from our learnings within the Innovation Center. We actually tried to minimize our instrumentation that we use for the control of the process. And essentially, all we use is pH and pH control, essentially. And we know our airflows that we put into the system, so we try and keep that steady. So if you know what airflow that comes in, you know what removal rate you're going to do, essentially, and we just control based on pH. So it's a really reliable, robust instrumentation and a really simple way of controlling our ANITAMOX process, which again shows that, it seems a little bit scary, new technology, a different way of doing things, slow growing, all that kind of stuff, but it's actually quite a simple solution. There are obviously other ways of controlling it, but that works quite well for us. Yeah.
Great, thank you so much. I think everything must have been crystal clear because that was the last question we had, and pretty much right on time as well. So thank you all for joining us today. If you have any other questions, of course, you can reach out to any of the three of us. You also have your team there, the local VWT team there in Australia, and many of you probably know Karen Shaw, who wasn't able to join us today, but please reach out to Karen if you have any questions, or of course, any of the three of us, you're welcome to contact as well. So thank you very much, and everybody have a nice evening.
Awesome.
Thank you. Bye-bye.
Thank you. Bye.
Bye-bye, Justin.
See you guys. Bye. See ya.
Bye.